So hello friends, in today's video we are going to discuss about 980 nm pumping and 1480 nm pumping difference. So all of you know that we use two types of pumping, 980 nm and 1480 nm pumping in EDFA amplifier for EDFA amplification. So what is the difference between 980 nm and 1480 nm pumping? Why we use 980, why we use 1480 nm pumping? What's the difference, what the mechanism of these two pumping? We will discuss in detail about these things. So let's start. So before knowing the difference between 1480 and 980 nm pumping, we should know the amplification mechanism, how the alpha amplification happens when 980 nm pumping is used and when 1480 nm pumping is used. So let's start with alpha pumped with 980 nm laser diode. So as we all know that 980 nm wavelength photons have more energy than 1480 nm wavelength photons. So when the laser diode pumps the erbium ion with a 980 nm pump photon, the electron in the ground state N1 absorbs sufficient energy and jumps into the excited state N3. As we all also know that higher frequency has higher energy, it means 980 nm pumping has more energy than 1480 nm pumping. So this is the main difference between 980 nm and 1480 nm, that when we use the 980 nm pumping, the electron have three energy state, N1, N2, N3, and when we use the 1480, it will use only two energy state. So we will discuss in detail about 1480 later. So let's concentrate on 980 nm laser pumping. So I have made these symbols to indicate what's the meaning of these symbols. So this, you can see the green one is for incoming input signal. This brown one is for 980 nm pump photons. Red one is for non-radiative emission. This yellow one is for emitted photons by spontaneous emission. N1, N2, N3 is for energy level 1 ground state level, energy level 2 metastable state level, and energy level 3 unstable state level, or you can say N1 is the lower energy and N3 is the higher energy level respectively. This dotted line you can see here, this dotted black line indicates the absorption, this brown one indicates immediate emission, this blue one indicates spontaneous emission, and this pink one indicates the stimulated emission. I have made a separate video about the spontaneous and stimulated emission. You can go through that to understand about the spontaneous emission and in stimulated emissions. So here you can see N3, N2 is the energy level. So here the electron's state time in N3 is 1 microseconds and N2 is 1 milliseconds. You can see 1 millisecond is equal to 100 microseconds. So N3 has a very short duration uh, for which the electron stay in this energy level. So you can see here the lifetime of electrons in the energy state N3 is approximately 1 microsecond, which I have mentioned here, which is a very low. So after a short period of time, the electron in the excited state N3, you can see the electrons in the excited state N3 will fall into the metastable state immediately. You can see here after just 1 microsecond by releasing energy in the form of heat. You can see non-radiative emission. So here you can see that this is the incoming photon signals. This is the 980 nanometer pumping. When this pump laser is used, so you can see the electron is absorbed this energy and moves to the higher energy level. And here you can see from a higher energy level N3, it immediate moves to the metastable state, or you can say it immediately transfer from N3 to N2 by radiating, by emitting non-radiative emission. You can see here this red one. The lifetime of electron in the metastable state or excited state N2 is greater than N3. You can see here this is the 1 millisecond. So many electrons get populated here in N2. Electrons absorb the energy, go to the N3 level, go to the higher energy state, and move from N3 to N2 and expend some times here, because this here the 1 microsecond times spent the electrons, and here 1 millisecond is spent. So electrons moving fastly from N1 to N3 and N3 to N2 and collect here N2, and this state is responsible for the population inversion. So in such case, the population of metastable state N2 is greater than, you can see, the state of N1, and this condition is called the population inversion, when the number of electron is higher in the higher energy state than the lower energy state, and this situation is called the population inversion, and this is very important for the amplification process. After some time, the electron in the metastable state N2 will fall back to the ground state N1 by releasing its energy in the form of photons. The process of emission of photon is called the spontaneous emission. Why? Because these electrons from N2 automatically, without any effect of incoming photon signal, is automatically moved from N2 to N1. So that's why it's called the spontaneous emission. The photon emitted due to the spontaneous emission will not travel in the same direction of the incoming photon signal because they are very random. They are not in the phase, or you can say the direction or the energy with the incoming photon signal. So that spontaneous emission does not contribute in the amplification, but it generates a noise, and it is the main cause of noise in the EDFA. You can see here, this is the spontaneous emission, this yellow one. Emission emitted photon by spontaneous emission, and you can see this is not in the same energy phase or direction with the incoming photon signal. The photon emitted from metastable state N2 will interact with the other metastable state electrons and force them to fall back to the ground state N1. The incident photon interact with other metastable state electron and force them to fall back to ground state N1. In both the above process, two photons releases at the wavelength of 1550 nanometer, and this process is called the stimulated emission, because you can see when the incoming photon signal interacts with the electrons in the higher energy state, then it will force this electron to move from N2 to N1, and this electron moves from N2 to N1 by the effect of these electrons. That's why the emitting photon is in the same direction, energy, and phase with the incoming photon signal. And this stimulated emission helps with the amplification. So this is the amplification process of 980 nanometer laser pumping. And you can see here, the likely was million of photons are released by stimulated emission, because this is the continuous process. Pumping is continuous. The electrons move from N1 to N3, and this whole process happens continuously, and millions of electrons or billions of photons uh, emitted by this stimulated emission, you can say, and thus the amplification achieved. So let's start the amplification mechanism by 1480 nanometer laser diode. So I have already mentioned that 1480 nanometer, when we are using this laser diode, there are only two energy state, because 1480 nanometer pumping has not sufficient energy to move the electrons from N1 to directly to N3. So there is only two state of energy, and hence there is no any population inversion incident happens in this. You can see here, we know the population inversion cannot be achieved in a two-level energy system. However, 1480 nanometer laser diode will pump the photon directly to the metastable state. So in 980 nanometer, you can see that the pump photons move the electrons from N1 to N3 directly. But here, by using 1480 nanometer laser diode, it will pump the photons directly to the metastable states. You can see here, this is a 1480 nanometer pump photon. When it is absorbed by these electrons, it will go to the N2 metastable states. The photon emitted from 1480 nanometer laser diode will interact with the metastable state electrons and force them to fall back to the ground state E1. The incident photon interact with other metastable state electrons and force them to fall back to ground state N1. In both the above process, the two photons are released at a wavelength of 50 nanometers. You can see. Likewise, millions of photons are released by stimulated emission. The wavelength and the direction of these released photons are same as the input light signal. You can see when the electrons in the N2 state and when the incident input photon signal interact with these electrons in the higher energy state, it will fall back from higher state to the lower state and release the photons with same energy level, phase, and direction. So it helps in the amplifications. And when the electrons automatically move from N2 to N1, it will create the spontaneous emission. And when the spontaneous emission interact with the other photons, then it will stimulate the electrons move from N2 to N1 as well. So this is all about the 1480 nanometer laser diode pumping amplification. So the main difference is it has two energy level diagram, and 980 nanometer pumping had three energy level diagram, and the population inversion happens in the energy level, which has the more than two energy level systems. So let's start 980 nanometer versus 1480 nanometer pumping EDFA. So we will see the main difference between main difference between these two pumpings. So 980 nanometer 980 nanometer pumping gives less noise than 1480 nanometer pumping. Unlikely 1480 nanometer pumping, 980 nanometer pumping cannot stimulate back transition to the ground state. 980 nanometer pumping also gives a higher signal gain, the maximum gain coefficient being 11 dB per milliwatt. The inversion factor almost becomes 1 in case of 980 nanometer pumping. The 980 nanometer pump needs 3 energy level for radiations. 980 nanometer pumps needs less electrical power compared to 1480 nanometer. Typically, 980 nanometer pumping results in a noise figure 1 dB lower than that for 1480 nanometer pumping. The shorter wavelength results in less noise. Quantum mechanism puts a lower limit of 3 dB to the optical noise figure at high optical gain. 980 nanometer pumping provides a value of 3.1 dB, close to the quantum limit. Wasted energy because electron must relax unproductively. Higher G. Narrow absorption band. When we use the 1480 nanometer pumps, 1480 nanometer pumping gives higher noise than 980 nanometer pumping. 1480 nanometer pumps can excite the ions directly into the metastable state. 1480 nanometer pumping also gives the maximum gain coefficient 6.3 dB per milliwatt. The inversion factor of 1480 nanometer pumping, the best one gets is 1.6. 1480 nanometer pumps needs more electrical power compared to 980 nanometer pump. So you can see the power, it needs more power than 980 nanometer pumping. Typically 1480 nanometer pumping results in a noise figure 1 dB higher than that for 980 nanometer pumping. The shorter wavelength results in less noise. Quantum mechanism puts a lower limit of 3 dB to the optical noise figure at high optical gain. 1480 nanometer pumping gives the value of 4.8, and you can see it gives a value of 3.1, which is very uh, close to quantum limit. Need higher drive current, high heat dissipation required expensive, smaller G, and you can see larger tolerance in pump wavelength around 20 nanometers. So let's continue. Erbium doped fiber amplification, essential components in optical communication system. They amplify optical signal in the 1550 nanometer wavelength range, which is commonly used for long distance fiber transmission. The choice of pump wavelength significantly affects the performance of EDFAs. Let's explore why 980 nanometer and 1480 nanometer pumps are commonly used for EDFA. 980 nanometer pump advantage. You can see higher gain and low noise figure can be achieved by when you're using the 980 nanometer pump. Advanced pumped at 980 nanometer exhibits higher gain compared to those when we use 1480 nanometer, especially for short EDF length up to 5 meters. Lower noise figure, the noise figure measure of signal quality is lower than using a 980 nanometer pump. It's particularly for alpha length up to 10 meters. 980 nanometer pumps are widely used due to their superior noise figure. They are commonly employed in C-band alpha. These pumps are suitable for compensating signal losses in distributed optical fiber sensor and long distance communication systems. 1480 nanometer pump advantage efficient power conversion L-band ADFAS, and consideration you can see although 1480 nanometer pumping provides higher optical power conversion efficiency, it is less commonly used due to the other advantage of 980 nanometer pumping. The wider separation between the laser wavelength and pump wavelength in 980 nanometer pump reduces noise compared to 1480 nanometer. So 980, when you use the 980 nanometer pumping, it creates less noise than 1480. Backward pumping with 1480 nanometer creates higher noise figure, while forward pumping generates lowest gain value. In summary, while both 980 nanometer and 1480 nanometer pumps have their merits and demerits, 980 nanometer pumps are preferred for most applications due to their better noise performance and gain characteristics. However, 1480 nanometer pumps still find use in specific scenario like L-band ADFA, etc. The gain of 980 nanometer pump is higher than 1480 nanometer up to 5 millimeter EDF length and for longer length. it becomes vice versa. 980nm pump cause a lower noise figure than 1480nm for EDF length up to 10 meter, and it becomes vice versa for longer length. Bidirectional pumping shows the highest gain value, and the forward pumping presents lowest noise figure for each pump. Moreover, backward pumping creates the highest noise figure, and forward pumping creates the lowest gain value. So these are all about the 980nm and 1480nm. Thanks for watching.